this problem, we're going to chapter 2 of Young and Freedman, and we're doing question number 75. So chapter 2 is one-dimensional kinematics, or motion in one dimension. And we've gone for a fairly tricky problem. I mean, we might as well use these videos to solve some of the more tricky problems that aren't just a matter of plugging in the numbers. So in this question, we've got two stones, and they're thrown vertically upwards from the ground. And one has 3 times the initial speed of the other. So if the faster stone takes 10 seconds to come back, how long will the slower stone take? And if the slower stone reaches a maximum height of h, how high in terms of h will the faster stone go? And we're assuming free fall. So the only acceleration we're going to deal with here is the acceleration due to gravity. So let's set up the problem first of all. So the two stones are thrown with different speeds from the ground. So basically we've got the ground level here. The stones are going to go up, and they're going to come back down again under free fall. So in this case, as usual, we've got the option to put our y equals 0 point wherever we want. In this question, it's probably most convenient to set y equals 0 at ground level and work from there. So we're going to use a fair bit of notation, and we have to keep track of the notation in this question. So y is going to be equal to 0 at ground level, and y is going to be positive going upwards. Okay, so we've set our 0 point, we've set our positive direction for this problem, and we'll say for the faster stone, we're using subscript, subscript f. Okay, so for example, vf would be the velocity of the speed of, doesn't really matter which we use in this case, the velocity of the faster stone, and then for the slower stone we'll use vs. So for slower, so we'll just leave this over on the right hand side here, just to sort of remind you of what the notation means, what the f and the s means, and so on. So we've got our two stones, we've defined our coordinate system, and now we need to set up the problem. So we need this is one-dimensional motion, constant acceleration, so we need the constant acceleration of motion equations here. In particular, these two apply, so you should know these fairly well. So y is equal to y naught. You would be more used, I suppose, to seeing these in terms of x, but we're looking at the y direction here. So y is equal to y naught plus v naught in the y direction times t plus 1/2 a in the y direction times t squared. So that's the first acceleration of motion, or sorry, the first motion equation we're going to use, and we'll just call that number 1 in case we have to refer back to it later. And the second equation that we're going to use is that vy squared is equal to v naught y squared. So vy squared is the velocity in the y direction, and that's going to be equal to the initial velocity in the y direction plus 2 times the acceleration in the y direction multiplied by y minus y naught, which are the heights or the y coordinates that we're interested in. So there are two equations of motion that we need to use for this problem. So let's go on from there and figure out what do we know, what other information do we know based on those equations of motion that are going to allow us to solve this problem. So we'll just move up a bit here. So we know that the initial velocity of the faster stone. So initial velocity, hang on, let me go back. Let's use black here for this one. So the initial velocity, v naught, and again we're using the subscript of the faster stone, is equal to 3 times the initial velocity of the slower stone. Okay, so that's the first piece of information that we can take from the problem, if you like. From what's given us. So the initial velocity of the faster stone is 3 times the initial velocity of the slower stone. Fine. Now, how can we use that information and use the two equations of motion to try and help us solve this problem? So we have this first equation of motion here. So we have this guy, and we can rearrange that to tell ourselves, in terms of the acceleration in the y direction, we can say that the y component of the acceleration, and that's the only one we're interested in this problem, is equal to minus 2 times v naught y over t. And you may be wondering, where did I get that from? How do I know this? Well, it's just a simple matter of rearranging the equation and solving it for ay. So in this problem, there's no y0 because we've set y0 at ground level. And then all we have to do is solve this equation for ay, and that gives us this equation that I've just written in black here on the slide. Now, both stones have the same acceleration, right? We should realize that the acceleration, let's write this in explicitly in red. So ay is the same, and we'll just write it in English, is the same for both stones. So sometimes it's good, to, even though this is a mathematical type of question, it's good to write in what you know in English and have it there in the page and help your brain process what's going on. So ay is the same for both stones. So what does that mean in terms of this equation that I've just written? Well, it means that we can equate things for the faster stone and the slower stone. And let me go back to black here. And when we equate things for both stones, we get v0 f, which is the initial velocity of the faster stone, over the time it takes for the faster stone, is equal to v0 s, the initial velocity of the slower stone, times divided by the time for the slower stone. So because ay is the same for the faster and the slower stone, we can basically equate the two and cancel out what we can cancel out, and this is what we get left with. So now we can solve for the time taken by the slower stone to complete its journey. So we'll just put implies. So that implies that the time for the slower stone is equal to the time for the faster stone multiplied by v0 s over v0 f. So this, again, we're just rearranging this equation that we had just here. And we know that the time for the faster stone is 10 seconds. It takes 10 seconds to complete its journey. And v0 s over v0 f is 3. So we have that, 1/3. So the velocity of the slower stone is 1/3 the velocity of the faster stone. So that gives us an answer of 3.33 recurring seconds for the time it takes for the faster stone to complete its journey. So 10 seconds for the slow stone and 3.3 seconds for the fast stone. So for the second part of the problem, I've just taken a little break and rewritten the second equation of motion that we had above. So vy squared equals v0 y squared. I should put a y in there as well. Let me get my pen back. Is equal to 2ay times y minus y0. And the key thing to realize here is that at the maximum height, so if you throw something up and it's in free fall, at its maximum height, vy here is equal to 0. So let's say vy at max height equals 0. So now we can solve this equation in terms of the acceleration in the y direction, as we did the last time, and we get ay equals minus v0 y squared over 2y. Let's put our y in here. Now, again, the acceleration for both stones here is the same. So that allows us to make an equation the same way as we did in the first part that's quite similar. So now in this second part, what we get is v0, and let me make sure my notation is right here, for the faster stone over y is equal to v0 s squared, which is the slower stone, over ys. So when we solve this equation, the second equation of motion, in terms of the acceleration, we realize that the acceleration is the same for both stones, so we can equate the conditions for both stones. That allows us then to write an equation for the maximum height of the faster stone in terms of the velocity of the slower stone. And that gives us v0 f over v0 s squared. So that's our equation that allows us to ratio the heights. And we know that v0 f over v0 s is the initial velocity of the faster stone over the initial velocity of the slower stone, which is, as we were given in the question, 3. So when we square 3, we get 9. So the height achieved by the faster stone is 9 times the height achieved by the slower stone. So that gives us 9h, and that solves the second part. So this problem, you need to understand your equations of motion well. You need to keep your notation in check, and you need to, I suppose the key point is to realize that because the acceleration is the same for both stones, they're the equations that you can use to bring the parameters together and solve these problems.